Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you all to this session. This is second class of fluid mechanics. In yesterday's class we covered the topic hydrostatic pressure. We will be extending this discussion and we will talk about the force exerted by fluid on the wall of container, and we will extend this discussion to Archimedes principle also. So without losing any further time, let me share my screen with you guys. Okay. So here we go. So yesterday we were talking about the pressure variation in accelerated container. So now let's take the problem of spinning container. Okay. Say we have a closed container here. Okay. And let's say some liquid is filled inside it, and its density is say rho, and let's say this whole container is being rotated with angular velocity omega about this axis over here. Okay, so since the any element of the fluid will be accelerated, okay, as it is undergoing circular motion about about this axis over here, so the motion here is accelerated in horizontal direction, so there would be a horizontal pressure variation as well. For example, if we wish to find out the pressure difference between any 2 points in the liquid, for example P1 and P2, say P2 minus P1 we want to find out. Okay, but this pressure variation, you must understand, is not a linear. First of all, how we will be finding out this pressure variation? For that, let's take an element of liquid over here. So let's say this element is at distance x, okay, and small extension in this x is dx. So the width of this element would be dx over here, and let's say this is of uniform cross section, so its area is a. Okay, the area of this container is a over here. So now let's say the pressure at this interface would be P, and the pressure at this interface over here would be P plus dP over here, as P is function of X. Okay, so because the pressure here is P, the liquid from this side would be exerting force in this direction, and that would be P times A, and the liquid from this side will be exerting force in this direction, that would be P plus dP times A. As you know, the pressure, the force due to pressure is compressive in nature. So this element of the liquid is getting compressed from both the sides. So effectively, if we do the force balance of this element over here, okay, so the force balance will be the net force in the leftward direction will become dP times A, and that would be equal to mass of this element into the acceleration of this element. So obviously this element is at distance x from the axis, so it will be accelerated towards the axis, and the magnitude of acceleration is going to be omega square x. So mass here we can write, so mass times acceleration. So mass here we will be writing mass of this element is rho times volume of this element, and the volume is going to be a into dx. So that is mass, and acceleration is omega square x. Okay, and a both side will get cancelled. So if we wish to find out the pressure difference between point 1 and 2, what we need to take, the lower limit say is x1, and the upper limit, let's say, is x2. X1 is the distance of point 1 from the axis, and x2 is the distance of point 2 from the axis. So in order to find out the pressure difference delta P, which would be P2 minus P1, we need to integrate this term, which is rho omega square x dx, and that would be from x1 to x2. So this will be simply giving us P2 minus P1 is equal to half rho omega square into x2 square minus x1 square. You should notice, okay, that the pressure is increasing. Pressure inside the liquid is increasing as we go away from the axis. That clearly you can see the pressure at point 2 is greater than pressure at point 1. Okay, so this relationship we will be using frequently. You must understand the pressure at any point depends upon the distance from its axis. So basically, in other words, you can write this expression P at any point will be equal to half rho omega square x square, where you must understand where x is perpendicular distance from axis of rotation. So that's the idea. So let's take a few problem on that concept. Say we have again some YouTube. Okay, obviously this YouTube has two limbs, and this YouTube, let's say, is rotated about this axis with angular velocity omega. Okay, and let's say this distance here, the distance of one limb from the axis is x1, and the distance of another limb from the axis is x2. And if the liquid is filled in this U tube and the tube is not rotated, like this tube is not accelerated, then we have understood that the level of liquid in both the limbs will be identical. But since it is rotated, so there is a horizontal pressure variation over here. We can say that the pressure at this point and the pressure at this point will not be same. Okay, clearly you must understand, if this is P2 and this is P1, since this point 1 is at smaller distance from the axis and point 2 is at larger distance from axis, so analytically simply we can say that P2 would be greater than P1. Okay, so one thing you must understand, since the pressure here is greater, it will push the liquid to a higher level in this right column, and here since the pressure is small, it will push the liquid to a lower column. Okay, here, so this would be the case over here. Okay, so that is how you can analytically say. So let's say this height is h1 and this height is say h2. So difference in the level, let's say delta h, if we want to find out, that would be h2 minus h1. So can we find out h2 minus h1? Definitely we can. So like the pressure difference between these 2 points would be let's try to do it systematically rather than jumping to the conclusions. So since we are at learning stage, so what I will be doing, I will be inside the liquid, I will be moving from this point to this point, let's say through this path. Okay, and let's say this point is A and this point is B. We must understand that PA is equal to PB. How is that? Because point A as well as point B are exposed to atmosphere. Okay, so wherever the surface is exposed to atmosphere, its pressure will be equal to same as atmospheric pressure. So PA is equal to PB. So I must move from A to B from within the liquid. So like say for example, following this path first, okay, the pressure will increase, and it will increase by you can say rho g h1. Okay, it must increase by rho g h1 over here. Okay, and from this part to this path, from to till center, if we are moving, okay, so then the pressure will decrease, okay, as we are moving towards the axis by a amount of, you can say, half rho omega square into x1 square, you can say. Okay, and uh, what we must say, the pressure variation I am equating. So from here to here now pressure will be increasing. So that would be half rho square into x2 square. Okay, so we are here now, and as we will go up, it will be like rho g minus rho g h2, pressure will be decreasing, so that will be equal to 0. So just rearranging this equation, what I will be getting is rho g into h2 minus h1 will be equal to half rho omega square into x2 square minus x1 square. You can say rho will get cancelled, so simply h2 minus h1 would be omega square by 2g into x2 square minus x1 square. Okay, let's extend this discussion to one another problem of a rotating or spinning cylindrical container. Say, let's say this is a cylindrical container, and this container itself is rotating with angular velocity omega. Okay, so here if the liquid is inside that, and if the liquid is static with respect to container, the liquid as well will be rotating with angular velocity omega. So let me tell you, if that happens, okay, the open surface of the liquid will take the it will take the shape of the paraboloid. And if this is x-axis and this is y-axis, so if we take the projection of this paraboloid on xy plane, it would be a parabola. Let's say this is parabola, or rather let's say let's take this as x-axis. Okay, so that this bottom or this lowermost point of the paraboloid becomes origin. And now we are interested in writing down the equation of this parabola. Okay, this parabola over here. So what would be the equation of this parabola? So this we can find out using two methods. I will be discussing here two methods. So one method is simple. Let's take any point P whose coordinate is x comma y. So obviously the open surface is the locus of all the points where the pressure is equal to atmospheric pressure. Okay, so we must understand at every point in the surface the pressure is going to be atmospheric pressure. So here the pressure would be atmospheric pressure as well at origin. So if we move inside the liquid, let's say by x in radially outward direction, and then by y in vertically upward direction, from this point to this point, from O to P, the net pressure variation gonna be 0. So from O, let's say this point is B, so from O to B the pressure will be increasing by half rho omega square x square, and that will be equal to, or you can say from B to P it will be decreasing by rho g y over here, and net pressure variation is equal to 0. So just by rearranging we will be getting y is equal to omega square by 2g into x square. So that definitely is a parabola. Okay, three dimensionally when you will be looking at this structure, that is a paraboloid. So now the another method which I was talking about was using the force balance. So as we have already understood, the net force any particle or any element of mass of liquid on the surface will be experiencing, so the open surface is gonna be perpendicular to that net force. So if this particle we choose on the surface, so this is the particle, so this is mg, it would be experiencing some weight, and it will also be experiencing some centrifugal force. So you can say that would be m omega square x. So we can very well say that this would be the net force. You can say m times g effective. Okay, and the perpendicular to this, like this would be the tangent at the surface. So if this angle is theta, so this angle would be theta as well. So very clearly we can say that tan theta will be equal to uh, here simply we can say that would be g over here, and tan theta, the slope of tangent at that point, this slope is basically dy by dx Okay, and that will be equal to omega square x by g. And just by rearranging, like dy is equal to omega square by g into x dx, etc., when you will be integrating that from 0 to x and that from 0 to y. So this simply will give you again the same relationship. Y is equal to omega square by 2g into x square. Again, same relationship we have got, but this time by another method. Okay. So using this property over here, let's try to do some problems by using the properties of paraboloid. Some property of paraboloid we will be discussing. So let's say this is the question. So let's say this is a cylindrical container of, let's say total height is h, and some liquid is filled in it to a level of height small h. Okay. And we wish to rotate this container. We wish to rotate this container with angular velocity such that, okay, so that liquid surface touches the brim. Let's say this will be the case. I want this to happen. Okay, like this is the axis of cylinder, for example. Okay, so we want this point, like this point over here, to touch the brim without the liquid really spilling out. Okay, so for that we can use the some definition, some properties of paraboloid. So one property I'm going to mention over here. Let's say this volume, that is the volume under the paraboloid, okay, and the volume above the paraboloid, means for example this volume over here, these volumes are going to be equal. Okay, these volume are going to be equal over here. Okay, so let's say this is some y. Okay, so if this volume is equal, let's say this volume is V1 and this volume is V2. So V1 is equal to V2. That is a property of paraboloid. You can geometrically derive it also. So that would be equal to the total volume of the cylinder of height y. Let's say the radius is say r. Okay, so that would be total volume would be here pi r square into y, and that divided by 2 over here. So this thing we are going to use. So the idea here is, if like we want the surface of the liquid to touch this brim over here without the liquid spilling out, so that means the empty volume here, this volume, must be equal to the empty volume over here. So that is how by equating we can find out the result. So let's equate. So how much is the let's say if r is the radius, so how much is the empty volume over here? So that is simply going to be pi r square into capital H minus H. So that is the empty volume in this case, and that will be equal to empty volume in this case, which would be the half of this volume, this quantity over here. So that is going to be pi r square by 2 into y. So what is going to be y? So we have looked at the equation of parabola. So y is going to be equal to omega square by 2g into x square, and x is basically r over here, so r square over here. So pi r square by 2 into omega square by 2g into r square. So solving this equation, we will be getting the value of omega is equal to 2 by r root under g times capital H minus H. So that was one simple question we did. So we have discussed the concept of a spinning container as well. So basically we have learned like how the pressure will vary in a liquid inside a container if the container is, for example, non-accelerated, and in the case of accelerated one, we looked at the case of linear acceleration as well as when the container is spinning as well. So now let's move on to the next part. In the next part, we are going to discuss, since we have already discussed that the liquid will produce some pressure at any given point. So wherever it is coming in contact with any other body, it will exert some compressive force on it. Okay, so extending this discussion, we are going to discuss force due to liquid on wall of container. Okay, so the general idea is, let's take a container of any random shape. Okay, let's say this is the container, and say some liquid is filled inside it. Okay, so here we can say that this liquid is in contact with the wall of this container at several points. You can look at this here. So liquid is exerting force, perpendicular force, you can say, on the wall of container. You have to realize that this force is going to be immediately perpendicular to the surface. Now we are interested in finding out the net force exerted by the liquid on the container. Okay, so obviously we must understand, like, if we consider the force balance on the liquid itself, so the liquid is in equilibrium. Okay, so the container wall must be pressing the liquid from all around, like this. uh, these arrows I have defined, like, as the force exerted by the liquid on the container. Equal and opposite forces at every point will be exerted by the container on the liquid. So it is obvious that considering horizontal equilibrium, and horizontally only the container is applying a force on that liquid. So considering the horizontal equilibrium of this liquid, we can say that the net force applied by the container horizontally, okay, in horizontal direction on the liquid, is equal to 0. So net force applied by the liquid on the container along horizontal will also be 0. So first thing we must realize, F horizontal is equal to 0. The force exerted by the liquid on the wall of container in horizontal direction, net force, or you must write net also, that is going to be 0, considering the equilibrium of this. So now if we consider the vertical in vertical direction, okay, so let's try to write the equation of equilibrium of this element of liquid, okay, which is inside the container in vertical direction. So what all forces are acting? So I have already said that the container wall will be applying some force, and that will be equal and opposite at any point. That would be force exerted by, equal and opposite to the force exerted by liquid on container. This is this direction I have drawn, that is opposite. Okay, so, and apart from that, you must understand what all forces this liquid body is experiencing. So one is its weight, which would be in, say, vertically downward direction. Okay, that is the weight of liquid. And apart from that, you must realize that atmosphere is also pressing this. So let's say if this area is, say, A1, okay, so the atmosphere P ATM into A1 is uh, a force exerted by the atmosphere on this liquid. So if we collectively draw the free body diagram, okay, and let's draw it separately. P, you can say, one force W, weight of liquid, will be acting in downward direction, and some P ATM, or let's simply write FATM, that would be in downward direction. And we don't know right now whether the force exerted by the uh, force exerted by the container on the liquid will be vertically upward or downward over here. Like, can we say that here? So that would be simply just by looking at the direction of this. So the net force exerted by the by the container on the liquid is going to be vertically upward direction. Vectorially, we can simply write force exerted by the container on the liquid, or force experienced by liquid due to container, plus weight of liquid, plus force exerted by atmosphere on the liquid. The vector sum of all these is going to be equal to 0. And just by looking at this equation, using the direction of arrows also, this very simply can be treated as force exerted by the liquid on the container. The magnitude wise, it will be simply weight of liquid plus force exerted by the atmosphere. Let's take some example also. So say we have a truncated cone of say this shape, okay, and say liquid is filled in it up to brim, and let's say the area of the upper surface is A1 and the area of the bottom surface is A2, and let's say this height here is H, okay, and let's say volume of the liquid which is inside this container is V. First of all, we want to find out the net force exerted by the liquid on the container in the vertical direction. So that would be as good as finding out the net force in vertical direction exerted by the container on the liquid. Okay. According to Newton's third law of motion, it will be equal and opposite. So first we will like to find out that quantity. So considering the equilibrium of forces, first of all, the atmosphere will apply a vertically downward force. Let's say that would be PATM into A. Okay, and apart from that, this will experience its weight, and weight would be nothing but, let's say density of liquid is rho, so that would be rho into V would be its mass into G. Okay, so the net force applied by the liquid, or net force applied by the container on the liquid, FLC, let's write, that would be in vertically upward direction, and its magnitude would be nothing but the sum of these two quantities, and that is going to be simply PATM into A1, okay, plus rho VG. Now let's say we are interested in finding out like what would be the force exerted by the slant wall of the container, okay, on the liquid. Let's say for example, you must understand like the force exerted by the slant wall on the liquid will be having such a direction, and you must realize its horizontal component from all around will cancel each other, so only vertical component will be left. So I am interested in force exerted on the liquid due to wall of container, this quantity I wish to find out. So if we have found out FLC, now see, like force exerted by the liquid, force exerted by the container on the liquid would be a force exerted on the liquid by the wall of container, and plus force exerted by the on the liquid by the base of container. That would be vector sum of these two quantities. Okay, so now in order to find out force exerted by the wall of container on the liquid, we do not need to write down the pressure everywhere and integrate and take the vertical component, etc. No, that is not required. We can simply use the force balance over here. That's the beauty of this part over here. So first of all, we must try to find out this part. Okay, how much force is exerted by the bottom of the container on the liquid? So that is going to be in vertically upward direction, and that is rather very simple. So we can write the pressure over here. So first of all, the pressure at this point would be P ATM, and since it is at the depth of h, so that is rho gh. Okay, and that multiplied by A2 will be the force exerted by the bottom. So this much force is exerted by the bottom. So the remaining force, like the remaining vertically upward force, so magnitude wise, force uh, ex- on the liquid exerted by the wall of container, it will turn out to be the total force, that is this, which we have already calculated, that is nothing but P ATM into A1 plus rho Vg, and we must subtract this quantity from this, and that would be P ATM plus rho Gh into A2. So that is how we are going to do that. So that is one of the problems. Okay, similarly, I am not going to solve that, but you can try this question also. Okay, let's say this time the shape of truncated cone is like this and liquid is filled in this, and let's say this area is A1, this area is A2, this is height some h, and the liquid density is rho. So can we now find out the force exerted by the slant face or the wall of the container on the liquid? So now you must realize this force will have a vertically downward component. So in the previous question it had the vertically upward component, but here it will be having a vertically downward component, and just by doing the force balance you can find out. So you just have to do the force balance on the element of liquid. So what all forces are acting? It's weight and the force due to ATM and force due to the bottom you can say, and this force which is exerted by the wall of container. So taking the vector sum of all these quantities, this quantity you can calculate very well, this quantity is known to you, this quantity is known to you, let's say volume is V, so only unknown will be Fw. So my intention here is to tell you, so whenever you are required to find out the vertical force exerted by the liquid on the slant wall of the container, you are not required to integrate. You can simply use the force balance and you can find out its weight. So that's one of the idea. So we have talked about the vertical force. So let's also talk about the horizontal force on one of the wall. Okay, so the idea here is, say, horizontal force due to liquid on wall of a dam, let's say dam. So let's say we are having a wall, say dam, wall of dam, okay, whose dimension, let's say its height is h and its breadth is b. Okay, and at one side of the wall there is say water body. Okay, and let's say the density of water is rho. So I wish to find out first of all, like what would be the net force exerted by the liquid, net force exerted by the liquid on the wall of this dam of this dimension over here. And another thing I am also interested is, if this is point O and this is, let's say, some axis passing through point O, so if this water body is exerting some force, it will also be exerting some torque on that ball, let's say about an axis passing through O, this axis. So we wish to find out the net force and net torque about O. Okay, so in order to do that, what we must be doing, see, on the wall vertically the pressure will vary. Okay, so pressure is not constant. So what we must do, so at a depth of h, okay, the pressure at this point would be like, the pressure we can write, that would be nothing but P naught plus rho g h we can write. So this will be the pressure. So due to this pressure at this level, okay, everywhere at this level the pressure would be P naught. So let extend this slightly by dh, and let's try to find out the force exerted by the liquid on this small elemental area. Let's say df we try to find out. Okay, so df will be nothing but P into dA, and P is nothing but P naught plus rho gh into dA. This area element is going to be, this strip is of width B and its height is dh, so that is going to be BdH. So net force will be the integral of this from 0 to h. So when you will be calculating, there will be two terms obviously, that would be P naught into P naught into B into H, that would be one term, and the another term would be rho GB into H square by 2. Okay, rho GB into H square by 2. Okay, so now you have to realize, like, let's divide these two terms. Let's try to understand about these two terms. So this is the wall of container. So throughout this depth, P naught pressure will will be present everywhere. So due to this, like, two component of forces, P naught into B into H, so that is due to, you can say, the atmosphere, effectively due to atmosphere, and that is transferred to the liquid, and liquid is exactly applying the force on it. Okay, this is not the force exerted by the atmosphere, that is force exerted by the liquid. Okay, only, and only the weight of atmosphere has been transferred onto the liquid, and this is the variable force over here. So you can say, you can treat it like, first of all, this is the constant part, like, that is P naught into uh, simply the area of the wall, and this another term can be also written as pressure at you can say center of area, pressure at center of area into total area. What do I mean when I say this term, pressure at center of area? So center of area would be the midpoint of the area somewhere, and at the midpoint of the area would be definitely at height h by 2. So what would be the pressure? Like, here you must understand, pressure at center of area is going to be rho g, and center of area is going to be at depth h by 2, so that is going to be h by 2 over here. So if you substitute this over here, and this a you already understand, that is going to be h into b, so you will be getting these two parts. Okay, and now I am interested in finding out, this would be the net force, and I am interested in finding out the net force, the point of application of forces over here. The point of application of this force would be some place else, and this force would be someplace else. So since that is a constant force, like, you can say that that does not depend upon at how much like, point of application of this point will not depend upon, let's say, for example, if we find out the net torque, so net torque due to this component and net torque due to this component I wish to find out. So tau1 would be simply, you can say, everywhere the force is same. So that is basically, you can say, due to this component, P naught B dH would be the force. So P naught B into P naught into B into dH is the force, and that multiplied with the arm. So arm would be nothing but from the bottom, it will become capital H minus H. And when we will be integrating this term from 0 to H, okay, so that would be simply be becoming P naught into B into, you can say that would be, its result would be P naught into B into H. So that would be simply H square by 2. So a point of application. So point of application of this force will be effectively, you can say, this tau 1 by F1 over here. So tau 1 is P naught B H square by 2, and that divided by F1, so that we have already looked at, so that is P naught into B into H over here. So this term and this term will get cancelled. So what effectively we will be getting is H by 2 over here. So if this term we say that is F1, and this term, let's say this is F2 over here. Okay, so the point of application of F1 is going to be here. So this is F1, and that would be at height h by 2 from the bottom. And now for the second term, let's say tau 2, let's try to find out. So dF was equal to rho gh into BDH. Okay, so that is the force, and the arm would be capital H minus H, and we will be integrating it from 0 to capital H, and this result we will be getting is rho GB into H cube by 6 we will be getting. Okay, and the point of application of this force over here would be nothing but tau 2 by F2. So tau 2 is basically rho GB H cube by 6. Okay, and that divided by F2, which we have calculated already, rho GB into H square by 2. This turns out to be H by 3 over here. So now you see. So effectively what we can say, so two forces, let's say this was the depth. So F1, first of all, F1 was acting at the midpoint, and the magnitude of F1 was nothing but P naught into the total area, that was nothing but B into H. Okay, so that is the force that is acting over here. And the another force, which was F2, you can say, this height is at H by 2, you can say. And this force, the magnitude of this force, which is acting effectively at H by 3, the magnitude of this F2 is rho GB into H square by 2. So why I have uh, done this type of calculation in this question, why I have treated these two forces separately, is going to be clear when we will be dealing with the next problem here. So let's try to discuss one problem. Okay, so say this is, or rather take it here, this is wall of some dam, and two different liquids, let's say one liquid is here and another liquid is here, or rather take different heights. Okay, so some liquid of density rho1 is filled to a height of say h1, and some another liquid is filled to a depth of h2. Okay, so this is the case. I want to find out the net torque exerted by this liquid on the wall of this dam over here, this torque about this. So in order to find out the torque, one thing we can do, we can take the integration like from here to here and here to here, two separate parts. But as we have discussed in the previous theory, that we can find out the a point of application of different forces. Okay, so first of all there would be the force due to the atmosphere, like this PATM you can say. So what would be the point of application of that? So that is going to be simply at the center of this wall, somewhere here, or you can say at a height of h1 plus h2 by 2. So that is going to be somewhere here. And what would be the magnitude of this force? The magnitude of this force is going to be equal to P naught, that is the pressure, and the total area of this wall, that is going to be h1 plus h2 into, let's say, breadth is b. Okay, so this is one of the force. And now let's come down, like here the force due to ATM we have already considered on the wall, and force due to this liquid over here would be effectively acting at this point at a height of h1 by 3 from the bottom, and the magnitude of this force is going to be rho g b into h1 square by 2. I hope you remember this result. Okay, and now you see this part here, like whenever any point you are going to write the expression for pressure, there are going to be two terms. One term would be going to be rho 1 gh1 plus rho 2 gh. Okay, so basically when we are trying to find out the effective force due to this liquid on this wall of container, we are going to have two parts. One part would be the constant part, due to because every point in this is going to be experiencing rho 1 g h1 pressure. So this is going to act somewhere here at the middle of, like for example, this height is going to be h2 by 2, and this force is going to be the constant pressure would be rho g h1, and that we can multiply it with the area of this wall. So that is going to be h2 into b. So that is the another force. And one another force which would be acting at h by 3 from this height. Okay, and that would be equal to rho g b into h2 square by 2. So all these forces would be acting 1 2 3 4. Okay, and we have found out effective point of application of all those forces. So we are now ready to find out the net torque, and net torque here due to all these would be in clockwise direction, you can see. So let's work from the very bottom. So the force is rho gb h2 square by 2, and its arm is h by 3 plus, okay, due to this force it would be rho g h1 h2 into b, and its arm is nothing but h2 by 2. And now due to this force it would be p naught into h1 plus h2 into b. Okay, and its arm is nothing but h1 plus h2 by 2. And the force due to torque due to this force would be rho gb h1 square by 2, and its arm is going to be from here to here, it is h by h2, and from here to here it is h1 by 3. So you can say that would be h2 plus h1 by 3. So this will be giving you the expression for net torque about an axis passing through, say, O. Okay, so this is one of the problem. Another problem I'm going to discuss is for the horizontal force only. Let's say we have some cylinder. Let's say cylinder we are having of dimension, let's say its radius is r and its length is l. Length is like say inward you can say, and its radius is r. And let's say this is kept on the surface, and at one side some liquid is filled to a height of say capital H, and the liquid density is rho. So now I am interested in finding out the net horizontal force exerted by the liquid on this cylinder, and also I want to find out the net torque exerted by this liquid on this wall over here. Here I'm going to ignore atmospheric pressure. Okay, so I will be only considering the pressure due to liquid as rho gh over here. I will not be taking atmosphere. You can take that, there is no problem, but this is the condition of question I'm providing to you. So you must understand, like this wall or this liquid would be exerting force on the wall of this cylinder in immediate perpendicular direction over here. So this force will have a horizontal as well as vertical component. So some people might be thinking we need to integrate. No, we do not need to integrate. We just need to do the force balance like we always have been doing. So now let's consider an element of liquid like this. Okay, here, which is immediately in contact with this cylinder. So this is the liquid. So now consider the horizontal equilibrium of this section of liquid. So horizontal equilibrium of this section of liquid, you must understand there must be some horizontal force exerted by the remaining of liquid here. So that is going to be let's say F1, let's say. And see, since using red arrow, I have shown the force exerted by the liquid on the cylinder, equal and opposite forces would be exerted by cylinder on the liquid. And let's say its horizontal component is F2 in this direction. So considering the equilibrium of this thing, consider the equilibrium of this thing, you must understand, like equilibrium of this liquid over here. So F1 is definitely going to be equal to F2. So F2 that we were looking for, because see, the red and uh, blue arrows are opposite of each other. So F2 will be the magnitude of horizontal force exerted by the liquid on the cylinder as well. And that is what we were looking to find out. So F2 is going to be equal to F1, and F1 we have already learned in this part. Okay, how to find out the value of F1, and F1 would be equal to the average pressure or the pressure at this projected area. This area we can find out. So the area here, so the average pressure would be simply rho g, and the pressure at the midpoint would be rho g h by 2, you can say. So that is the average pressure, and this area, the area of this projection, okay, is going to be h into L. Okay, so this is a force. And if you also want to consider atmosphere also, so this is going to be equal to, say, P naught into area, and area obviously is equal to h into L. So that is not only the force exerted by uh, liquid on the cylinder, equal and opposite, since according to Newton's third law of motion, equal and opposite force will be exerted by the cylinder on the liquid, okay, in the opposite direction. And remember, this force we have calculated in horizontal direction. So this was some part where we discussed, okay, force exerted by the liquid on the bodies in contact. So like how we have divided this discussion in horizontal component and vertical component. And my objective here was to avoid integration in all those calculation as much as possible. We have been just trying to balance the forces on a segment of liquid. Okay, and in case of the horizontal force, we tried to divide the forces into several categories, and we tried to find out the point of application of all those forces, such that we can find out the net torque exerted by the liquid on that. So being said that, one other interesting question I want to discuss here, I was also interested in finding out the net torque exerted by this liquid, let's say about point O. So about point O, you must understand torque about O. You must understand the forces, the line of forces, see, is going to be perpendicular. So all these forces which will be acting on the cylinder will be passing through the center. Okay, so all these dfs, you can say, if you write df over here, the line of force is passing through this point O. So this will not be producing any torque. So net torque about point O due to liquid on this cylinder is going to be zero. So this is also one another result. So now let's quickly move on to Archimedes principle. Today I have very less time left, but here in this time I will introduce Archimedes principle. So the statement simply says that if a body is fully or partially submerged in a fluid, it will experience a force due to liquid known as buoyancy. Buoyancy will be equal and opposite of effective weight of displaced liquid. Okay, here I have used effective weight and equal and opposite of that. So what I mean to say over here is this, like say let me first justify this situation. So say we have some liquid of density rho, okay, and say we have some submerged body. So we have already understood that the liquid will be exerting some compressive force on it, okay, from all around. So the net of this force is nothing but buoyancy. Net force exerted by the liquid on the submerged body is same as buoyancy. Basically, both are same thing. So while solving a question, you must not, while drawing a free body diagram, you must not draw like buoyancy and force exerted by the liquid separately, because they are both one and same thing. Okay, so do not double count. So first of all, this thing, so we are interested in how much force will that be. So in the very first theory which I had discussed, like see at all the points on this surface here, okay, a pressure profile is going to be created, and that pressure profile will only be due to liquid. Means whatever is inside, like whatever is this material over here, I'm not interested in that. This pressure profile will depend only upon the surrounding liquid. Okay, so the force exerted by the liquid will not depend upon the submerged body itself, but will only depend upon the external liquid. Now see, if that is the case, if we replace this space over here by the same liquid of density rho, so we can very safely say that liquid that will be in equilibrium, if that is another some other body, it will be it will not, it might not be in equilibrium. Okay, but this, if we assume it to be liquid itself, okay, and it is surrounded by the liquid, same liquid from all sides, we can safely assume it to be in equilibrium. So now let's consider the force balance on this. So this segment of liquid is going to experience what all forces. So first it would be like a weight of this liquid. Let's say this is segment 1, and the surrounding liquid we can say segment 2. So this would be W1, and uh, so so the remaining liquid will be exerting some force, okay, which will be to balance this W1. So that force here is going to be effectively in upward direction. So that is basically force exerted by 2, exerted on 1 by 2, F12 you can say. So you can clearly see, according to the equilibrium, W1 is nothing but F12, you can say, that is equal to 0. And this F12 is nothing but buoyancy. Okay, so W1 plus buoyancy, the vector sum is going to be 0. So this buoyancy is nothing but minus W1. Okay, and that is nothing but uh, negative of weight of displaced liquid. Okay, if this system is accelerated, let me or say I will discuss this part in the next class, since we have already exhausted our time. So let's end this lecture. We will be continuing in next lecture. Okay, so thank you for joining us.